Hi everyone, this is Mrs. J. Today we are going to learn about sums of infinite geometric series and recursive rules, but first please pause the video and give this warm-up a try. Alright, go ahead and check your work. So here we have a finite arithmetic sum, so here's our formula for that, the information we need, and then I plugged it in here to get my sum. And then this is a finite geometric sum. So for that we use this formula. Here's the information we need, and here is my sum. So that's a really large sum. For both of these, we're adding up 20 terms. So this would definitely be something that you would want to use the formulas for rather than listing them out by hand and adding them up manually. So now that we know how to do sums of finite arithmetic and finite geometric series, we're going to talk about how to find the sum of an infinite geometric series. So you may be wondering, well, if a series is going on infinitely, how could there possibly be a sum? Doesn't it just keep growing or getting more negative? So the answer is that this will only work for very specific cases. So you actually can find the sum of an infinite geometric series if your common ratio, the absolute value of your common ratio, is less than 1, meaning that r is between -1 and 1. So if you have this specific condition, essentially what's happening is your terms as you continue on are going to get closer and closer to 0, and they become so infinitely close to 0 that essentially they're not adding anything to the overall sum. So we do say that we can find that sum. So this has a formula just like our finite series. You need the first term and the common ratio. That's all you need. And you have to make sure, again, that the common ratio meets the specification for an infinite sum. And that sum is simply your first term divided by 1 minus your common ratio. And then if you notice that that common ratio is greater than 1 or less than -1, then we would just simply say that the sum does not exist. All right, let's give these a try together. So here I see that I have a geometric sequence rule. Here I have an infinite sum. So I'm going to see if I can use my infinite sum formula. The one thing I need to check is my r value. So here you can see that our r value is 0.7. And since the absolute value of r is less than 1, we can, in fact, find this infinite sum. So there's my r value. Remember, to find my first term, we can always just plug in 1, and it's 3. So now we're just going to plug those into our sum formula. So we have 3 over 1 minus 0.7. For these, just to keep it exact, sometimes it's easier to think of this as in fraction form. 1 minus 7/10 is 3/10, and that ends up just being 10. So the sum of that infinite geometric series is actually 10. All right, let's try this one. Here it's not in summation notation, but I see that it's a series because I have the plus signs, not commas, and I see it's an infinite because I have this ... So for this, I'm going to start by checking for a common ratio to make sure it is, in fact, geometric. And I do see that it is geometric. However, because r, which equals 3, I see that r is greater than 1. We know that there is no way to find that infinite sum. So we can write does not exist. And again, that's because our common ratio is greater than 1. And if you look, if you just kept adding up these values, they're not going to approach any number. It's just going to get infinitely larger. So hopefully that makes sense. All right, let's check this next one. First, I'm going to look for a common ratio. I see from here to here, I'm multiplying by -3/4. Here, I'm also multiplying by -3/4. Same here. So I can see that my r value is -3/4, which The absolute value of r is less than 1, so I know that I can find this sum. And then I can see that my first term is 1. So I'm just going to use my infinite sum formula. So 1 over 1 minus negative 3/4. So 1 over, so this is 4/4 plus 3/4, which is 7/4, which gives me a sum of 4 over 7. And there you go. So please just remember that you do need to check that your common ratio meets the requirement to use this formula, but once you have checked that, all you need to do is plug in a sub 1 and r, and you are good to go. All right, please pause the video and see if you can try these on your own. All right, go ahead and check your work here. So for the first one, our r value is 0.2, so we can find the infinite sum. So I plugged in my information, I got a sum of 5. For part B, my r value is 2/3. Remember, you can always take any term and divide it by the term before to find your common ratio, which I did here. And 2/3 is less than 1, so I can I can find this infinite sum. So I plugged in my information, and my sum is negative 18. But for part C, you'll notice that the common ratio is 5 over 2. Because that value is greater than 1, this infinite sum does not exist. Okay, so now we're going to transition and we're going to start talking about a different way that we can write rules for sequences. So far, everything that we've been writing, when we write our rules, they have been explicit rules, meaning that each term is described in terms of its relative position, right? All of our rules have n in it. And we have never specifically named it, but those are called explicit rules. So now we're going to learn a different way to describe them, and that's called recursively. So we're going to make a recursive rule. And a recursive rule describes each term in terms of one or more previous or preceding terms. So, for example, we might notice a pattern that you take the term before and you add 5. We can actually write it recursively that way with a symbol like this, a sub n minus 1. So a sub n means the term, the nth term, so a sub n minus 1 means one term before. And if you see a statement like a sub n minus 2, it means 2 terms before. There's a really famous sequence called the Fibonacci sequence in which you add up the previous 2 terms to find the next term. So in that case, we would have to use something like this. So with these recursive rules, we're going to be describing the next term in terms of the term before. You take the term before and you multiply it by 2. You take the term before and you subtract 5. So again, it's just a different way of writing these rules. All right, so now let's take a look at what these recursive sequences look like and how we can use them to list terms. So here we are told that a sub n equals a sub n minus 1 plus 4. It's essentially saying take the term before it and add 4. Now, since we're referring to the term before, we have to have a starting place. We need to be told at least the first term. So that will be part of our explicit rule. If you're not given the first term, how do you get started? Because what's the term before? So here we are told that a sub 1 is 1. So that's our first term. We're going to find the first 6. So to find a sub 2, right, if I'm using my recursive rule, it's a sub 2 minus 1 plus 4, which is just a sub 1 plus 4. Meaning the term before it. So if I want the second term, I take the first term and I add 4. So 1 plus 4 is 5. And again, I just pulled in this and I substituted it there. Now to find the third term, I do a sub 3 minus 1 plus 4, which means I take the second term and I add 4. So here I'm taking this term, which is a sub 2, and I add 4. So you can see that to find the fourth term, I would just take the third term, a sub 3, and add 4. So I'm taking the term before it, and I'm adding 4. To find the fifth term, I will use the fourth term, and I'll add 4. So I get 17. And for the sixth term, I take the fifth term, the term before it, and I add 4, and I get 21. So again, everything is written in terms of a previous term. Now let's look at, oh, and we can see that this was an arithmetic sequence, right? I'm just adding the same number. I'm adding 4 to get to the next term. That would be my common difference. Now let's look at this one. This is also a recursive rule. It's just written a little differently. Instead of saying a sub n, it says f of n. So f of n equals 3 times f of n minus 1. This means the term before. So I'm simply taking the term before and multiplying it by 3 to get to the next term. And again here, they give us the first term. So my first term is 1. My second term is simply 3 times f of 2 minus 1. So again, 3 times the term before, which is f of 1. So f of 1 was 1. 3 times 1 is 3. So to find f of 3, I'm going to do 3 times f of 2, the term before. So 3 times 3 is 9. For f of 4, I'm going to do 3 times the term before, which is f of 3, which was here. I'm going to multiply that by 3, and I get 27. For f of 5, I'm going to do 3 times f of 4. So I'm going to do 27 times 3, and I get 81. And for f of 6, 3 times the term before it, which was f of 5, and I get 243. So there are my first 6 terms. So that's how you can evaluate a recursive rule. All right, go ahead and pause the video and give these 2 a try on your own. All right, go ahead and check your work here. So for this first one, you're just taking the term before it and multiplying it by 1/3. So I'm just taking the term before, multiplying it by 1/3. The term before, multiplying it by 1/3. And then for the second part, my first term is 23. And this just means take the term before it and subtract 6. So for f of 2, you just take f of 1 and subtract 6. For f of 3, you take f of 2 and subtract 6. So then you just keep subtracting 6 from there. So now we're going to practice writing these recursive rules. I think writing recursive rules is actually easier than writing explicit rules, because you're literally saying take the term before it and just either add or subtract or multiply or divide. So you just need to be able to recognize a common difference or a common ratio. The one thing to remember is that you do need to define a sub 1 as part of your rule. Okay, let's give these 2 a try. So first we need to try to figure out what type of rule this is. So I'm going to look for a pattern. I see that this one has a pattern of adding 10. So it is arithmetic. So if you look at what we're doing, we're literally taking the term before it and adding 10. So we can write this explicitly. First we'll define our first term, and then we'll say any term, a sub n, is the term before it plus 10, and that's it. That's all there is to it. All right, let's look at this next one. So here I see that there's no common difference. However, I can look for a common ratio. So let's see if a common ratio exists. So if I have 40 over 16, and I simplify that, I would get 5 over 2. Let's check a few more. What if I have 100 divided by the term before? 10 over 4 is 5 over 2, and I can see that that pattern holds. If I multiply by 5 over 2, I get the next term. So that will be my common ratio. So that means I'm literally taking the term before it and multiplying it by 5 over 2. So again, just make sure we define our first term, and then we say any term. is simply going to be the term before times 5 over 2. So I could say 5 over 2 times a sub n minus 1. Or you can say a sub n minus 1 times 5 over 2. Either way, it means the same thing. All right, go ahead and pause the video and give these two a try on your own. All right, go ahead and check here. So this first one is an arithmetic sequence. The common difference is 5, so you literally take the term before it and add 5 to get to the next term. And for part B, this is a geometric sequence. The common ratio is 1/2, so you can find any term by taking the term before and multiplying by 1/2. And please make sure you have defined a sub 1 as part of your recursive rule. All right, the last thing we're going to do is we're going to turn an explicit rule into a recursive rule. So I see that this one is arithmetic. This is an arithmetic sequence. So for an arithmetic sequence, first thing I'm going to need to do is figure out the first term. So a sub 1, so 8 times 1 minus 6, which is 2. And then from there, I need to figure out what the common difference is. So I can look at the second term if it helps us. And here I see that I am adding 8. And maybe we remember from when we're making these that this number should be the common difference. So to write this recursively, I'm going to define the first term, and then I'm going to simply say any term can be found, so a sub n, by taking the term before, a sub n minus 1, and then adding 8. So now I've taken an explicit rule and I've written it recursively. Let's give the second one a try. I can see that this is a geometric sequence. So same thing, I'm going to need to find the first term, which is -3. And I know that the common ratio is the base of my exponential expression, so I can see that my common ratio is 1/2. So I'm going to define the first term, and then I'm going to say any term, or the nth term, is simply the term before it times 1/2. So 1/2 times a sub n minus 1. And there you go. All right, here is the last few tries, so please pause the video and give it a try. Okay, check your answers here. This first one is arithmetic. My first term is 25, and my common difference is -5. So you're simply taking the term before and subtracting 5 to find the nth term. And the part B is a geometric sequence. My first term is 7. My common ratio is 2. So to find the nth term, you take the term before it and multiply by 2. And please, again, make sure you've defined a sub 1 as part of your final answer. All right, that is all for today's video. Thank you so much for watching.